very short section. 5.5 about unitary operator, and the textbook is put it in the context of basis transformation, which is fine because we use unitary operator mostly as a transformation matrix that we talk about in chapter 4. It's the same thing. We transform from one set of bases to another set of bases. We use it this way, but it can also be just a ordinary operator, say, and we apply that to preserve some property. So the unitary operator has a property that it preserves the scalar product. So if you have a unitary operator, so U operate on F, whatever that is. So you can say it's F. Another vector is called F prime. And then U of D is D prime, right? That's just an operator. But if U is unitary, it means that U deck is equals to U times inverse. You have the inverse operator and the adjoint operator is the same. Then you can see that the F, like F prime and G prime, the scalar product is this U and then UG, right? And then just apply the definition of adjoint. So this is like move this to the left side. That U and U deck U is just U inverse U. So that U inverse and U is just identity, so it's FG. They preserve the scalar product if you have a unitary operator. And so this is transforming a vector to another vector. And so there's no basis transformation. So you can have a unitary transform operator just like any other operator. If you satisfy the unitary condition, then it preserves. After you transform all the vector respectively using the same operator, then it preserves the scalar product. That's one way to look at that, right? But now in the context of basis transformation, you can also have a unitary matrix. So you will see that if you express the transformation matrix as a matrix, this matrix is slightly different from the matrix representation of operated last term. So in this case, it's this U. If you have a basis, so phi I, then the U. If you express U as matrix elements in this basis, so U of mu. I think the text would like mu doesn't matter. Mu is phi mu of mu. But it's still defined like that within the same basis. You know. So this is a unitary operator that actively transform a function or a vector. But in another case that you can consider is you keep the same state or keep the same vector, but you express that, expand that in different set of bases. And you want to know how the coefficient of these under these two set of bases transform. And it turns out to be transformed by a unitary matrix also, but the matrix is not given by this element. You see that the matrix element is one is the old basis, the other is the new basis. And we see that before when we do a transformation of vector in chapter 4. We did that. The transformation matrix is the dot product between the unit vector in one basis and then the old basis and the new basis. You remember how we get the transformation matrix. All right, so we'll do that which is you see that this is similar. This is that matrix element also satisfies the unitary unitary condition. So basically now you have this vector psi, and so you have two sets of bases of phi I or phi mu, and then you want to transform it to in another set of bases phi pi mu. Right. So in the O basis, that is sum over mu and the coefficient c sub mu, right? And you know that the phi, all this c sub mu is simply the function that the projection of function on the basis, so it's fine. Right, this is how we get it. But then we want to express that into the new basis also. In that case, it's the C pi, some C pi. So it's the same function, the same vector expressed in two different sets of bases. Okay, so we'll do that because we can likewise express all this. So we can do it one way or the other. We can start from here to try to go into here, because that is so finally we want to get into that, but we try to get it to that by expressing all the old bases to the new bases, right? So that is what we can do. The old basis project on the new basis, right? But we need a sum. And now we use mu instead. Find mu pi, and then find mu, right? That and intensify, right? So this part is just how you express one basis function into the set of the new basis. Right? This is how you do it, right? Okay. Now you try to put it into this form, right? And, then because you finally sum over this and that, so you take this sum out, sum over mu, and then the rest is sum over mu. You can put this number first. Mu, right, and then finally, right. And so you identify this is your C sub mu pi. Actually, to make it the same form, this is sum over mu, right? This is sum over mu and mu. And to make it the same form, you can also just do the trick that we exchange mu and nu, because those are just dummy variable, dummy index, right? So you can change mu and mu. This is mu, this is mu, this is mu, right? And this is mu, right? And so this becomes our C sub mu pi, right? And this is originally this one, so this is just this one. So this is what we call the C sub nu, original C sub nu. So that the equation would be C sub mu pi equals to sum over new this object from new from new and multiply with C set new. Right. And now you see that this is just in the structure of matrix multiplication. If you regard this C sub new as a column matrix, and this becomes a square as column vector. This is a square matrix. Then this square matrix multiplied by a column vector give you another column vector C pi. So this is in the form of C mu C pi. If in the vector C equals to a matrix dot into C. Right. Okay. So this is your equation 5.69. Is okay. So now you identify this matrix element. This is your u mu nu. Right? This u mu nu is defined as 1 mu 1 mu. So it's different from what I just erased the original Unitary operator in the same basis. So this is just the scalar product between the new basis and the old basis. Okay, so that's how you define this. So this is not the elements of in a single set of bases. This is a dot product between the basis vector of the two set of bases. And we define this. This is just like what we have in the transformation matrix. I think a textbook pointed that out by referring to like the vector rotation in chapter 3. And that transformation matrix is also the dot product between the unit vectors in the new coordinate system and the coordinate system after you do the rotation. And that's exactly the same thing. All right. And now the requirement is that you can do the inverse of that. So you do the inverse basis transformation. You can supposedly you can recover that same. We call it. I mean, this because this is the changing from the non-prime base set of bases to the prime bases. Right? You can do the exactly the same and get the transformation from C from the prime basis to the non-prime basis. Basically, it's the inversing the whole thing. So you can say they're just changing prime and non-prime. So like C nu is just sum of the new. Now it's changing prime and non-prime. So phi nu and then phi nu prime. Right. Yeah. And now you have another matrix element, and this you can call it. This is a technical V, right? V. This is V. Yeah, this is V. Whatever. So let's just call it V. V. Right. So therefore, this the inverse is just C is this V dot into C point, right? And this V mu nu is obviously defined by this one. This U is defined by that one, right? And then we can use the property that of the scalar product. So let's write this. So this V mu nu equals to y mu line, and we apply the property of scalar product. We can exchange the two function position of two function and do a complex conjugate. Y mu prime y mu complex conjugate, right? And then by definition, this is just our u mu mu complex conjugate. So, and then this exchange that to mu, and then complex conjugate is just our that was adjoint. This is adjoint. Okay, so basically compare this with that. This is just adjoint. So V is just U adjoint. Right, C pi. Right, V is just U adjoint. So by this we show that V is just U adjoint. And then we apply this is the first equation again. This is U adjoint times U, right, times C. The C is equals to U adjoint dot into U dot into C, right? And because both are C, so we require that this is just identity matrix, right? So you show that the U adjoint is the inverse. So by this, you can see that implies U adjoint is the U inverse. U inverse, okay. And I'm keeping this vector notation just to indicate that this is not a vector or an operator within the same within a vector space that is usually defined. This is just a matrix element. This the matrix element and defined by the scalar product of the old basis and the new basis. Okay, so that is slightly different from the matrix element of other operator. Other operator, we put operator in sandwiches between the bases of the same set of bases. So this is slightly different. Okay, yeah. So that's how you transform the vector. Okay, and there's some example which is more tedious. So you can, anyway, it's straightforward how you do this. Do all this scalar product between all old bases and new bases, and that would involve integration. But because of involved integration is quite tedious to get the final U matrix in this example, but it's not difficult. So I'll let you read and struggle with that. You probably have a homework problem similar to that. Yeah, except that the table or the U representation. This example, I'm talking 5.5.1. If you have your textbook, you probably want to correct there's some sign error in the textbook, the matrix representation of U. Basically, all the I's of the wrong sign. I don't know. I don't know whether they correct it in other new print. So just be careful. So you read it or do your homework problem. You probably need to be a little careful. Do you have your textbook? Yeah. All these eyes are incorrect of the incorrect opposite sign. Okay.